Okay, so today we're going to get a quick introduction into logarithms and be able to solve some simple logarithmic equations. That's our goal for today. What a logarithm is, what it stands for, those kinds of things. So before we do that, some review from last time when we were solving exponential equations. Remember the whole point here was to get a common base on both sides. So exponent base, that is. So since the left side on the first one has a base of 4, I want to rewrite the right side as 4 to the third power. Then we can drop the bases, and x is equal to 3. Okay? Now, the second one, it's still the same goal, but we can't rewrite 27 as base 9 to a power. So we have to drop both of them down to a base 3 to a power. So 3 squared is 9. Since there's an x up here as an exponent already, I got to multiply. 27 is 3 to the third. We drop these bases, and so 2x is equal to 3. Divide both sides by 2, and x is 3/2. And the last one, 125, we can rewrite as base 5 to the third power, but the left side is 1/5, is a 1/5 exponent base, not a 5. So what we did, brought the 5 up and made that exponent a negative and multiplied that into the x. Then dropped the bases. We got negative x equals 3. Divide both sides by negative 1. And so x was negative 3. Okay? Now, here's the deal with logarithms. Right? So 2 squared we know is 4. 2 to the third we know is 8. But what if we want to know what power to put on 2 to get 6? 2 to what power is 6? Well, since 2 squared is 4 and 2 to the third is 8, that exponent must sit somewhere between 2 and 3. Right? It's going to be a decimal. But it's not very easy to figure out. And it's because of this that mathematicians decided to write that exponent, this x, in a little bit different way. And they called that different way a logarithm. A logarithm is nothing more than an exponent. It's another way of writing that x, writing that as an exponent. Okay? So what does that look like? How do we rewrite that as an exponent? Here it is. Exponential form to logarithmic form. A logarithm. Logarithm has a base just like an exponent does, because a logarithm is an exponent. As a matter of fact, the exponent base and the logarithm base are going to be the same thing. So here we have an exponent base of b. Here we write log base b, where that b is the subscript on the logarithm. Now, here's where things get a little bit crazy. The idea is to be able to pull the exponent down on the other side of this equal sign so that we are able to get that x by itself. We can solve for x. So what we do is we write a logarithm with the same base, so the base stays the base, but then, for example, the x and the y here switch. The x comes down on the opposite side of the equal sign, and the y comes over with the logarithm. So base stays base, the other two play switcheroo. And we got to be able to work both ways, going from exponent form to logarithmic form and logarithmic form to exponential form. How you read a logarithm. So the exponential form, of course, b to the x equals y. The log form, log base b of y equals x. Okay, that's how we read that. Log base b of y equals x. Okay, it's just a way of rewriting that exponent. This guy right here, log base b of y, is the exponent on the exponential form. It's just a different way of writing the exponent. Logarithms are exponents. Okay? Some things to understand. The common log. There is a common log. We count and we do our numbering system in base 10, right? All of our digits are powers of 10. Ones, tens, hundreds, thousands. Go through the decimals, tenths, hundredths, thousandths. So there's something called a common log. There is a common base to have on the logarithm, and that's 10. You don't need to write the 10 when you're wanting to talk about the common log. For example, this guy right here, log of 3 equals 1,000, is the same thing as writing log base 10 of 3 equals 1,000. Both of those have a base 10. It's just we don't write the 10 very often. Okay? All right. Let's get used to writing from logarithmic form to exponential form. Okay? Base stays base, the other two place switcheroo. What that means is the base of this logarithm is 5, so the base on my exponent is going to be 5. And then these two guys play switcheroo. That 5 needs an exponent, so I move the 3 over next to the 5 as its exponent, and the 125 goes on the other side of the equal sign. So 5 cubed equals 125. Okay? Same thing as 2. The base of this logarithm is 10, even though it's not written. So we go exponent base 10. These guys switch. So 10 to the negative first equals x. Third one here, the base is x. So base stays base. So your exponent base is x. We bring the negative 2 over as the exponent. And that's going to be equal to 1 over 100. Okay? Now, from exponential form to logarithmic form, I'm just going to go the other way. Going to work backwards. Base stays base. So since the exponent base is 9, I make this log base 9. The other two play switcheroo. So I bring the 81 over next to the log, and the 2 on the other side of the equal sign. This is another way of saying that exponent 2. Okay? Number 5, base stays base. So this is going to be log base 10. I don't have to worry about writing the 10. The other two play switcheroo. So the 1,000 goes here, the 3 goes on the other side of the equal sign. And 6. How would you write that? Take a second. Try to write it. Did you let base stay base? This is logarithm of base 194. And then bring the 14 over and slide the x on the other side of the equal sign. So log base 194 of 14 is x, is equal to x. Okay? Now, solving. How do we solve these? And we want to solve without a calculator. So at least without a scientific or graphing calculator that has a logarithm button on it. Okay? Well, here's the deal. We don't know how to evaluate logarithms yet. So the only thing that we can do at this point is rewrite an exponent. We know how to solve an exponential equation at this point. So let's rewrite this in exponential form. So base stays base. So the 9 becomes the exponent base. We bring the 3 halves over as the exponent on the 9 and slide the x on the other side of the equal sign. So now we have to find some way to evaluate 9 to the 3 halves power. Remember that a fractional exponent can be rewritten as a radical. This guy is the index on your radical. So we make this the square root of 9, and then we raise that to the third power. Square root of 9 is 3. 3 to the third power is 27. And that's how we work with our logarithmic equations right now. Just rewrite it in exponential form, right? So here, same thing. Base stays base. So 3 becomes the exponent base. I'll bring the 2 over as the exponent, slide the x on the other side of the equal sign. So x equals 9. Okay? Take a look at this one. Can you at least rewrite it? Give yourself a second and rewrite it. Okay? Did you make this 64 to the negative 4/3 power equals x? That's what you wanted to do. Now, this is a negative exponent. So we want to drop this base down to the denominator of a fraction, leaving our numerator to be just 1. Then we can rewrite our fraction exponent as a radical, making this the cube root of 64 to the 4th power equals x. The cube root of 64 is 4. 4 to the 4th is 256. Oh, wait. Sorry. This is all in the denominator of a fraction. Sorry. This is actually 1 over 256. Okay? All right. You give it a shot. Stop the video. Start it back up and see if you got it right. Right, so rewrite it first. Base stays base. This is 2/3 to the negative 4th power equals x. Now just evaluate that exponent. The exponent's negative, so I'm going to flip this fraction over first. And then raise the numerator and the denominator to the 4th power. So this becomes 81 over 16. Okay, hopefully you got that. Next. Still solving without a calculator. Again, rewrite this in exponential form. So, base stays base. This is base 7 raised to the x power equals 1 over 49. And now, again, we're back to our exponential equation. How do we solve that? Well, the 49 we can definitely rewrite as 7 squared. But I need that 7 to come up to the numerator so that my bases are exactly the same. And now we get x equals negative 2. Okay? Still the same thing. 11. Looks kind of hard. Nah, not too bad. Again, we're going to rewrite. Base stays base. So 49 over 36 still is the base for our exponent x that we're bringing over. And that's equal to 6 over 7. Now, I recognize that 49 and 36 can both be written as a base squared. So 7 squared and 6 squared. Now, remember that exponent rules apply here. If the numerator and the denominator are being raised to the same power, then we can pull that power out and just make that the exponent on the entire fraction. So pull that 2 out with the x and make this 2x. But if you look, our two bases still aren't exactly the same. We need to flip one of them over, and it doesn't matter which one. If I can flip the 7 over 6 over, I got to make this negative. Now we can drop bases, remembering that this has an exponent of 1. We get negative 2x equals 1 divided by negative 2. We got x equals negative 1/2. Kind of tricky. Okay? All right. Try 12. Rewrite that in exponential form, and then solve it, start the video up, and see if you're right. Okay, what'd you do? Remember the base here is still 10. So we get 10 to the x equals 10,000. We can rewrite 10,000 as 10 to the 4th. Drop those bases, and x equals 4. Okay? All right. More of the same. We're just going to slide the x. Oh, now one for you to try again. Sorry. So stop the video, start it back up, and check your work. Okay, there you go. 27 to the x equals 243. We can rewrite 27 as 3 cubed. So 3 to the 3rd power, but then multiply by the x, so get 3x. 243 can be rewritten as 3 to the 5th. So 3x equals 5, or x is 5/3. Okay? All right. Again, we've talked about fractional exponents before and how to handle them. When they're on a variable, it's a little bit different. We want the exponent on that variable to be a 1. So what we do is we understand that if we raise this to a power itself, then we have to multiply the exponents. Well, if we raise this to the 3/2 power, then these reciprocals will multiply out to 1, and we get x to the 1st. That means we also have to raise this guy to the 3/2 power also. So we rewrite this as the square root of 9 to the 3rd power. But also remember that anytime that we even root in an equation, and anytime we even root a variable, we have to include plus or minus. Okay, and we are even rooting. Anytime the denominator is an even number, that's an even root. So we have to actually include plus or minus here. So the square root of 9 is 3. So we get plus or minus 3 to the third power, which ends up being plus or minus 27. Okay? 15, kind of the same, only now the exponent's negative, and I don't want to move the x base so that the exponent is positive. I'm just going to go ahead and raise this to a negative 5/2 power to achieve my exponent of 1. I just got to remember how to handle 1/4 to the negative 5/2 power. Well, first of all, I'm going to flip the 1/4 over to make that 1 and make the exponent positive, so 4 to the 5/2. Don't forget that we have to, when we square root the 4, take our plus or minus and raise that to the 5th power. Square root of 4 is 2. 2 to the 5th is 32. And don't forget your plus or minus. Okay? All right, 16. Raise this to the 2 over 1 power, or just square both sides, right? Square 9, you get 81. We don't need a plus or minus because we're not even rooting the variable. Okay? So there, we're done. All right, so continue solving these logarithmic equations. Again, rewrite in exponential form. Base stays base. So this is x to the negative 2 power equals 1 over 36. Okay? Again, I don't want to move that x to get my positive exponent. I'm just going to go ahead and raise this to the negative 1/2 power, which is the reciprocal of negative 2. That multiplies out to 1. So now we've got 1 over 36 to the negative 1/2 power. Flip 36 over to get a positive exponent, and then square root, and don't forget your plus or minus. Okay? But something to keep in mind, we cannot have a negative base on a logarithm. Without going into a lot of depth here, it has a lot to do with sometimes it works to have a negative base and sometimes it doesn't. So we just go ahead and not worry about the study of negative bases at all when we're talking about logarithms. So what that means is that actually we can't use negative 6, because if you plug negative 6 in per x, that gives us a negative log base. So we just use 6. The negative 6 is an extraneous solution. Okay? All right. Number 18 looks like this. Again, rewrite this. X squared equals 25 over 9. We can square root both sides. Since we're square rooting both sides, we've got to do our plus or minus. Square root 25 and you get 5. Square root 9 and you get 3. But again, remember, our log bases can't be negative, and so we just keep the positive 5/3 as our solution. Okay? Try 19. Okay. Rewrite this. X to the 3/4 power equals 8. Raise both sides to the reciprocal. 4/3 power. That becomes 1. So now we get the cube root of 8 to the 4th. We don't need a plus or minus here because this is an odd root, not an even root. So this becomes 2 to the 4th, which is indeed 16. No problem with 16 being the solution. And so we're done there. Okay. Last but not least, give it a shot. Start the video up. Stop the video. Try it. Start the video up and see if you got it right. Did you get 343? Check out the work there. If that doesn't make sense to you, make sure you come in and get some help. Okay. Homework's out in Canvas. Have that done by next time.